Yep. Okay. You guys see my slides?
Yeah.
Yeah. I actually prefer to present in this mode because I have a 49-inch screen, and if I do the presentation mode, it puts the giant thing, and there's going to be too much gap on the sides. So uh
Sure. Sounds great. Looks good
yeah.
on our end, though.
All right, yeah. This should look okay to you guys.
Yeah, looks good, Atsu.
Okay. All right. Thank you very much to the people there for listening in, and the also Seth and others for organizing this workshop and allowing me time to talk about this work, which is using gravity data to estimate ice thickness on Taku. Um, I'm Atsuhiro Muto. I go by Atsu for those of you who don't know me. I'm at Temple University, which is in Philadelphia. Um, I'm presenting this, but this is the work that my former PhD student now, Louise Borthwick, did. She graduated last year. She's going back to UK. That's where she's from originally. Like the but she's been away on an extended trip, and the timing of things didn't work. So I'm making presentation on her behalf. And this is based on the paper that she published in Journal Glaciology just over a little year ago. So if you actually want to know the nitty-gritty of the work, please go and read the paper. Um, but the work or the data that went into the paper were collected in 2023 as part of JERP, where when Louise was one of the instructors. So huge acknowledgement to JERP, especially the students who actually collected the data and the field guides who led them safely, and also the Seth, Annie, and Brad for allowing us to carry out this work. Now, this is a table that's actually in the paper, and it lists the in situ geophysical observations carried out on Taku, and gravity surveys have been conducted over the past about 50 years. Most of them weren't actually published in peer-reviewed papers, but the data are there. Most of those are actually collected as part of JERP. Um, but starting in 2016, that's when I actually acquired a gravimeter as part of my startup package, starting at Temple. Um, uh, we've been carrying out gravity surveys. So in 2016, Kaya was the teaching faculty leading the gravity survey. And an interesting thing or cool thing is that Louise was actually a student at that time. And several years later, in 2022 and 23, Louise actually led the gravity survey as a faculty. So there are more data than that actually went into this, more gravity data than what actually went into this paper. But I believe the data from 2016 and 2022 weren't as good because it wasn't actually the gravity data. The GPS data weren't good for doing the elevation corrections. The data set is just from 2023, but doing the gravity survey as part of JERP has been a great experience for students, as far as I know. Um, so I'm just showing some of the slides that the students used in the presentation at the end of their time. They being clever about the naming of the group, like the milligauss, gravity units, so often in milligauss. Um, so they actually do um, the project during some of the processing and the gravity modeling during the JERP period, and here are some the results that they actually are able to come up with. So even though some of the data have not led to peer-reviewed paper, it's being very productive or very useful in mentoring students in geophysical methods. Right. So going back to this table, so I just talked about the gravity surveys, but there has been other geophysical surveys. So there's been seismic and some radar as well. over the past half century or so. But the coverage isn't complete, or there are a lot of gaps. And I'm showing this figure from Matt Nolan's paper in Journal Glaciology 95. There are some spots where he and colleagues imaged the bed, but the knowledge of the bed of Taku is mostly unknown. The um, so we would like to keep adding to that the data sets to actually get a better estimate of the ice thickness. Apart from in situ observations, there is a couple, at least a couple of the global glacier thickness data sets from the surface inversion methods, and I'm just showing the one on the right from the Farinoti et al. 2019 paper. Um, but the thing is, if you actually compare the ice thickness from that kind of the global surface inversion method, um, to the actual the in situ measured one. So taking the number from Matt Nolan's paper, and this is from seismic data, the maximum thickness at this location in the middle of profile 4 is 1400 meters, whereas the surface inversion methods in Farinoti et al. Gives 950 meters. So I think we all know that, and they do actually say this in their paper, but the surface inversion methods are often uh, not accurate or not accurate. So those are sort of motivations for doing more geophysical work. And another big thing is that this is actually what Renee showed yesterday is radar data are often difficult to interpret for the bed. So there are many of Icebridge airborne radar surveys have been done, but you can only pick the bed in limited places. And I believe that this is probably going to improve in the future with things like these clutter simulations, but still using different kinds of geophysical methods to obtain the ice thickness is good. So that is the big motivation for this work. So with gravity method, you measure the small changes in the Earth's gravity field caused by subsurface density variation. So things like valley glaciers are, well, at least theoretically, very good targets because you have this big contrast in density between the ice and the rock. So if you have a valley glacier, you typically have this um, negative gravity anomaly. So from that negative gravity anomaly, you can estimate the ice thickness. Okay. So the data that Louise used come from three profiles. So two across glacier profiles that what's called profile 4. Okay, here's Camp 10 and profile 7. And there is a long glacier a profile close to the middle of the glacier. So once you get the gravity measurements, you go through a series of corrections. And here's the list of the actual corrections that were done. So there's a bit of process going through all these corrections. And there are uncertainties coming from all these corrections. So that adds up to something like 0.808 milligauss. But the one thing I would like to highlight is that the repeat measurement. So there are some places where they went back repeatedly so that you could actually get a sense of the drift of the instrument, but also just the spread of the data. And that came out to be 0.15 milligauss, which is actually a little large for ground-based measurements. And I think that's because uh, you are carrying the gravimeter on the back and you're skiing around and you're setting it down, and it's just that the rough traveling conditions probably leads to this. Usually when you do ground gravity surveys just around here in like a normal like near urban settings, you get an order of magnitude better uncertainty. But the final uncertainty of the measurement we determined was 0.17 milligauss, which translates to the uncertainty in the actual the ice thick measurements of somewhere around 100 to 150 meters, something like that. Okay, so once you get the data, what you do is gravity inversion, where you will start with assuming some kind of geometry for the glacier. You photo model the gravity anomaly, you assess the fit, and you just keep doing that process. Then changing your model each time so that you get a better and better fit. So we're testing thousands of models of the glacier thickness and the geometry, and we've picked the ones that fit the data reasonably well or within the uncertainty. Okay. And the actual algorithm that we used is called very fast simulate annealing. Now, even going through all that, the gravity, the inversion, and because we didn't actually have a whole lot of data, it's just those three profiles. Ideally, you have sort of grid pattern data set, but uh, we didn't. So we had to assume um, some geometry of the glacier. So what we did was we used a V shape, U shape, and some wide U shape. And those are all functions or the power functions of the distance from the center of the glacier to determine these shapes. So we did gravity inversion assuming these shapes, then seeing what basically what the maximum thickness is in the middle of the glacier. Okay. Another thing we had to do is the actually account for the gravity signals coming from outside of the glacier. So um, the area within this orange is the domain of the gravity inversion, but you actually have to calculate what the gravity anomaly coming from the outside of the glacier, and for that we actually had to use the ice thickness measurement of Fahrenheit et al. So that I think was the biggest dilemma in using that the product. We know that it's uncertain, but we couldn't get away with it. So we actually do sensitivity analysis um, using sort of well sensitivity analysis to what the ice thickness estimate is outside of modeling domain as well. Okay. So diving into results, I'm going to be showing the results at across the three profiles. So starting with profile 4. Okay, so on top is the you have the results from the three assumed shapes, V, U, and wide U, and below you we're showing the measured gravity in black and the model of the gravity anomaly in the corresponding colors. And this yellow one here, that's the one from the surface immersion method. So that's the Fahrenheit et al. Ice thickness estimate. Right. So right off the bat, you can actually see that there's actually a big difference between the surface inversion derived ice thickness and the estimates from the gravity. But if you look closely, even the gravity inversion after carrying out the inversion process, it was actually struggling to fit the data off to the side. So there is a bit of a discrepancy here, or what we call a misfit off to the sides. So what we did was actually, after running through the inversion algorithm, manually perturbed. So we say, okay, well, if the gravity anomaly the model gravity anomaly came to be more less than the measured, let's put more ice so that that it fits the data better and things like that. And we estimate that the the shape of the valley, or yeah, the valley is that it's more of the wide and flat bottom, and there's a step-like feature off to the eastern side of this profile 4. Okay. Moving on to profile 7, and the upstream profile. Similar thing, okay. Big difference between the surface immersion method estimate and that the shape of the glacier is not a simple one, neither V, U, or wide U. There is actually another step-like feature, but off to the western side in this case, and it is more deepened on the eastern side. So the glacier is more asymmetric upstream. Okay. Moving on to looking at along the glacier. So this is one called longitudinal A. Okay. Um, Again, yellow, that's from Farinoti et al. And we have much deeper or the thicker estimates all along the profile. Okay. Um, and because of that, the non-uniqueness and also the large uncertainty in the gravity data, you actually end up getting quite a bit of the uncertainty in the final results and the difference in the ice thickness between the or among the different valley shapes that we assumed. But there's a couple of things that's robust in all of the results. Okay, well, one of them is that the ice or the bottom of the glacier goes above sea level at around where the branches, or this is the Mathis, I think, then this is the main Taku Glacier, where they meet is about where the ice goes, or the ice bottom goes above sea level, which is about 35 kilometers upstream on the current terminus. And the other thing is that all of these models show these two bedrock bumps. Now, just to mention about that uncertainty or the sensitivity to the what we had to assume about the amount of ice outside of the glacier. So, depending on if there's the underestimate or the overestimate of the amount of ice outside the glacier, of course, we end up actually basically this is shifting the ice thickness, and that leads to about plus minus 200 meters of the difference in the thickness, but uh, uh, where the whereabouts the ice bottom goes above sea level, and also these two bedrock bumps, those are robust features in all of these, and either way. Okay, and if we actually compare what we get solely from the ground-based gravity to the seismic measurement that's in Matt Nolan's paper. Okay, so he had a seismic profile going across profile 4, and his estimate for the deepest part across profile 4 was 1,400 meters. And in all of the inversion results with the different valley shapes, we get something pretty close to it, at least within the uncertainty to the seismically derived. So this is good. I thought it was almost too good, but this is what we got. So Renee talked about her deep radar results. So let's take a look at those. So I'm just showing what Renee gave me. This is part of what she showed. Going from left to right, in this case, it's going from upstream to downstream. But I have my profile. Our profile is showing going right is upstream and going downstream to the left. So I'm going to flip what Renee gave me left and right, and also I'm going to put a bit of a tilt to it. So I think this is the view that we get that is most comparable. So this is just by eye. I'm sort of trying to line up the features that I think I'm seeing. Okay, so I know that it's hard to actually pick the actual bed in this deep radar data, but I see these two bumps, which probably corresponds to the bumps that were resolved or modeled by the gravity data. But if we look at the thickness, we get around 1,000 meters for one of the bumps, and 1,050 meters for the second bump. And just by looking at what Renee gave me here, this looks like about 750 to 800 meters. So I think we're in the ballpark. But um, as Renee was saying yesterday, I think there's still probably some corrections need to be done. And also, who knows, this might not actually be the bed, it might be coming from the side. So I think there's room to, or there's opportunity to actually look at the two data sets and trying to figure out where the actual bed is within this radiogram. But I would say that we're in the ballpark, same ballpark. So, summarizing this work, the gravity data, from the gravity data, we were able to map these two bedrock bumps that weren't in any of the previous ice thickness and also the glacier geometry data sets. And if Taku were to retreat up to that part, they could actually be the places where the retreat could stabilize from potential marine retreat. Okay. And like I said, the bed likely rises above the sea level about 35 kilometers upstream of the current terminus. And a profile for the gravity estimate of the ice thickness is very comparable to that from the size to the ice thickness derived from the seismic data. Um, the gravity-derived thickness seemed to be higher than from the deep radar, but again, I think there's more room for improvement or the joint interpretation of the deep radar with other geophysical data sets. But the big thing is that the surface inversion methods do not resolve the bed features that we modeled. And also, it actually grossly underestimates the ice thickness, which leads to the underestimate of the potential sea level contribution from Taku Glacier. So I think continued collection of ice thickness estimates, not just from gravity but from radar and seismic methods, I think should continue. And um, perhaps that the kind of the data collection that was done as part of the job that led to this paper should continue, because I think it is really a valuable and useful lesson for the students. And we have, or Louise has shown that it can actually lead to a very good peer-reviewed paper. Um, but just throwing it out there and thinking about if there is a desire to continue or get more gravity data so that we could actually get the estimate of the ice thickness in a wider area. So airborne gravity surveys have been done in Antarctica and Greenland, but also in like Patagonia ice fields. So I'm just showing some figures from this Gourlet et al. Paper in 2016 that did airborne or helicopter-borne gravity survey in northern Patagonia ice field. So the scale of this is a little larger, and I believe it took 4 to 6 weeks of helicopter flying to collect a lot of data. They actually have a lot of survey lines. And I believe this kind of a survey will cost, well, some millions of dollars. So whether that's worth it or not is, of course, worth thinking about. But there it is. But there's been development in drone-borne gravimeter, and they are starting to become feasible, I believe. And I think that is going to be cheaper than the helicopter borne, because you don't have to hire the helicopter. And the instrument itself might be not cheap, but I believe this might be a path forward to doing airborne gravity survey if desired. So I'm just throwing it out there, but I think we have effectively shown that the gravity method is actually quite useful when other um, um, geophysical methods do not work as well as you hoped. So I think that's all I have. Right. Thank you.
Yes, Bobsy, thanks for that. It was great. You're you're touching on the drone-based work is perfect timing because I think Jeff is talking next about drone tech development and using the ice field. But so I'm kind of curious about, in the radar that, you showed work that, there's ice bridge data that Renee also showed with the challenges of clutter, airborne. And you have all those corrections you have to make, the latitude corrections and elevation correction, tidal corrections, things like that. Are there additional corrections I assume that you have to make in airborne survey that also make it problematic for gravity?
No, I think the correction, well, there is an extra correction called the ETVOS correction, which is correct for the turns and, basically the turns of the aircraft. But, that can be done. But I think the thing is, so how accurate or what's the sort of the resolution um, well, so sorry, not the resolution so much, but I guess the final uncertainty in the drone-borne gravimeter. So the airborne, it's kind of a milligal to 2 milligauss. Whether the drone-borne gravimeters can actually achieve that, I don't actually know yet. Um, I haven't seen any results. But as far as corrections, I think they're pretty much pretty well accounted for.
My only other comment on, I'm chuckling because there was also an additional attempt to do gravity in 2007, but the gravimeter was misplaced at that time. We happen to find it in Atland, British Columbia. And I know this because I was trying to do the gravity survey in 2007, but it did not happen. So I was really excited to see Louise get this data.
Yeah, misplaced as in like it
As
got
in it was
lost.
lost. They lost it from the prior year.
Oh, okay. Wow. But yes, I was really happy that Louisa is actually able to do as much as she did, and she really pushed in my opinion, the limit of what the gravity data can show, and also the processing in the gravity data. I've been sort of thinking about this and sort of attempting this myself, and I kind of failed. And I guess that's why you get PhD students
Yeah.
and you make them do it.
Any other questions before we move on? All right, thanks, Atsu.
All right. Thanks, everyone.